how would an application work if you wouldn't have concurrency, if everything were single-threaded? So let's say you have a server with an endpoint, and each request will take 1 second to complete. What will happen if I send to the server 10 requests? You will get a response every second, right? So if your application has to handle 1,000 concurrent users, the 1,000th user will have to wait for everyone before them. That wouldn't be right. So this is how a happy user looks like. Yeah, that's what he expects from his application, a quick response. But that's what many times happens. The first thing programmers thought about how to change this was to use threads and so-called worker threads. That would mean to delegate the work, to delegate the heavy work to other threads, and when they finish the jobs, just to notify the main thread that we have a result. So actually what is happening, while the server is active, he's listening for requests, and he handles the request to be processed by a worker thread. This is also a diagram. This is how it actually looks like. The most important thing we have here is that queue, because that queue can get you and will get you in a lot of trouble. Let's try something. Let's try to do the same experiment, this time with a worker pool, but it will still be single-threaded, just for demonstration purpose. So every request will still need 1 second to complete. We'll send 3 requests, and let's see what will actually happen. No, that didn't work as I expected. Just a second. Let's try now. Let's try to increase the time it spends, let's say 3 seconds. I will restart the server. What's going on? Now you have the worker threads, and you got a behavior which is much worse than the linear one. Why do you think you got all these 3 responses after 9 seconds? What is happening is the following. So basically, you have sent 3 requests. all those 3 requests were put in a queue. I will show you. And when the thread wants to send the response back to the client, it actually can't, because what he does, he is putting the response in the queue, and the worker pool, our threads, will take from that queue what's in front of it. So first in, first out. You will say probably, okay, this is happening because you use just a single thread. That was for demonstration purpose, but I can also use more threads. Let's say, so you can see here, if I'm going to the executors, you see Java is using a linked blocking queue in order to keep all the tasks which cannot be run in the available threads. All right. So let's make it, I don't know, 5. And now I will send 20 requests. Something is not working as expected. Let's try again. No. Oh yes, it's working. But you have exactly the same problem. Basically, you got a queue full of requests and responses, and it's not reliable. Regarding how many threads you have, you can have a pool of 10,000 threads, but if you have 20,000 requests, then you will get into the same problem. One solution would be to use a separate thread pool for the responses. That is one solution. The point really is you have to handle thread pools with caution. And this remembers me of a funny story. Do you use parallel streams? Do you like Java 8 parallel streams? That's pretty cool stuff. So when you have a big set of data and you want to parallelize it and get a quicker result, that's cool. But I was once called to a customer which had a problem. They were saying the application is slow. It's not delivering the responses back as they expected. But it was a brand new application. It was using all the latest technologies. And when I got there, the first thing I saw is they were having about 25,000 threads. And I said, oh my God, what is actually going on here? What they did, they used parallel streams, but like I mean everywhere. And they were creating all these threads. And then they were sitting in the same thread pool and with other tasks, and other tasks basically could not execute because all those little threads were in that queue. And actually all I had to do is remove from some places the parallel word, and the application was working just fine. So you have to know when you can parallelize and when you can't do that. Does that make sense? So basically, like I told you, even if you have a thread pool with many threads, you come into the same problem. You are using that queue, and that queue is what you would like to avoid if possible. Of course, you can, what you say, let's make more threads. But how many threads can you create? How many threads do you think you can create? That depends on your memory, of course. But there's also limitation on the Linux kernel, for example. And so you cannot create an indefinite number of threads, an infinite number of threads. Of course, when dealing with threads, you have also different problems. The context switching is very expensive to switch from one thread to another one. And when you have a lot of them, this will decrease your application performance as well. Resource consumption and thread contention. When you have many threads, what do? They just wait around to be able to access the CPU. How many threads can you actually run in parallel? Exactly how many cores you have. So if you have 10,000 threads and 8 cores, 9,994 threads will just wait because they can't do anything else. No, I won't go into this now. So this system is called parallel workers. Actually, you got the worker which does all the work received for one request. A reactive system tries something differently. You don't have a worker which does everything. You have more dedicated workers which work together and have to communicate in one way. Are you working with reactive systems? Java rigs, Project Reactor, things like that? No? All right. I hope you saw the benefit of it. Basically, there are two types of reactive systems. One of them is using workers which communicate through queues. And the second model is called the actor model, where you have different actors and they communicate sending messages to each other. One example would be the Akka framework. Has anybody used the Akka framework? Do you like it? Cool. All right. What I will show you today is something a little bit differently. So like I said at the beginning, I will show you how a reactive system essentially looks. And for this demonstration, I will use the LMAX Disruptor. The heart of the disruptor is this array. It's a circular array. They call it the magic ring buffer. The design should look very familiar. You have a publisher and a subscriber. That's basically the definition of reactive streams. It's just an array. You can put anything in it. It's just Java objects, and everything is controlled through each indexes, which are called sequences. When you first want to publish something to it, you go to the first sequence available. Of course, when you just start, it's at position 0. And afterwards, you just increment it. Yeah, what I didn't say, this array has a fixed size. So you have to initialize it at the beginning with a size which you don't think you measured it and suits your design. But the idea is when you get to the end of the array, it basically it's just moving forward around and around. In order to work with it, you have to do something very simple. You have an event publisher and an event translator. The event publisher is asking for the next available bucket where you can put something in it and send the object to the event translator, which will actually fill in that object, and the event publisher with call publish. It's basically a two-phase commit. All right. Another important thing about this array buffer, about this ring buffer, is that it's pre-allocated, being fixed size. And that is also very friendly with the garbage collector, because you don't, it's not a queue. You don't push things into it and don't get things out of it. All the objects remain there. But that also means that every time you put something at the sequence, at the index, you have to clean up the previous object. It would be a right thing to do. If you want to consume things out of it, you have a batch event processor, which actually takes the next sequence available. And all you have to do is to implement an interface called event processor, where you will actually handle all your events. One thing which is basically was very important for me is this ring buffer provides batching. So the batch event processor will ask, he didn't see anything in the ring buffer yet. He didn't consume anything. So he'll go to position 0, and he'll ask, do you have something at position 0? And the ring buffer will say, yes, I have, but I'm already filled up to 3. And you can quite safely take everything until the sequence number 3. Your event processor will still get everything one by one, but you will know when this end of batch is, and this information is actually extremely important. I will show you a few examples where this was actually a game changer. When the batch event processor has consumed from the ring buffer, he updates his own sequence number. So in this case, he got everything up to 3, and he will define his sequence number to 3. And next time he visits the buffer, it will ask, do you have something for me above 3? And the ring buffer will let you know if it has or not. If it doesn't, then it will say to him, please notify me. So it's completely event-driven. I think the best way to understand how it works is to go through an example. Let's say we would like to build a car. The car has an engine, has the driver's seat, the passenger seat, the rear seat, the doors. And after you have assembled all this, you can go and paint it, and at the end, you can put on the wheels. So basically, we can work on parallel on the engine and on the seats. It doesn't make sense to put the doors before we end with the seats. And it doesn't make sense to paint it before we have put the doors. And of course, the wheels, we can all work on parallel with it. So basically, you will define a few consumers from your ring buffer, like the engine handler, the driver's seat handler, the passenger seat handler, and the rear seat handler. They will all go in parallel. In this case, each one will run in its own thread. Another thing you can do, if you have not slower workers, but let's say the workers which are working on the engine, it takes longer for them. Then what do you do normally? You get more workers, you hire more people. So you can also use a worker pool which could take care of your engines. This sequence number does the whole magic. Because based on this sequence number, an event processor knows if he can touch a bucket from the ring buffer or not. So, for example, if you have the driver seat handlers, the passenger seat handler, and the rear seat handler, and you can see that the door handlers cannot get in front of the drivers or of the seats, because that wouldn't make sense. And you have this just with this sequence pairer. It's non-blocking. That's the most important part. This is the essential part. All this design is non-blocking. You don't have threads waiting for each other. Let me show you in the code actually how it works. It's extremely simple. So basically what I do, you have to define a disruptor, and you have to tell him who are its consumers. And of course, you have this nice composition where you can say, after one consumer follows the next one, and so on. I was mentioning this very nice batching. Let me show you what that means. This line shows us where a batch started and ended. So you can see in this time we have 3 elements in the batch, then afterwards we have just 1, then you have more again. If, let's say, your consumer, the most important part is in such a design if the consumer is slower than the producer. What do you do when the consumer is slower than the producer? There's no much things which you can actually do. But when you have this batching, you can really take the whole batch and work on it, rather than work on individual events. That's the benefit of this batching. And everything else is extremely simple. You just need to implement an event handler and then simply put your business logic on, call your services, and so on. What do you get with it? First of all, it encourages you to model your domain. Because you are not using a framework, you have to think about how would you like to parallelize things. So you are in charge of your domain model. Freedom. Freedom for the programmers, because you don't have the boundaries which come with heavy frameworks. Why are we using frameworks, actually? Because we think they keep us safe, and most of the frameworks are also very useful. The one I don't like is where companies are building their internal frameworks and you have to work years with them. Probably you know this situation. Encourage creative thinking. You can go truly parallel, but with very few threads. You get high cohesion and low coupling, because you design your model in such a way that you have all those components. So you have the engine, you have the rear, you have the doors. So you have very reliable ordering, and it's very beautiful to compose. And like I said at the beginning, it's easy to understand and very easy to change. It's resilient, exception handling is very easy, and it can be very fast. Actually, it was built out of a necessity in order to be able to process a huge amount of events, of requests. And it follows completely the reactive manifesto, which says application has to be responsive, message-driven, elastic, and resilient. The architecture looks basically like this. When you have a microservice, you put one of the ring buffers at the edge of your application. So at the start, you can group all your requests in it. At the end, where you put all the responses, and if you have I/O calls or external calls, that means your business logic is interrupted, and you should put such a buffer also inside your application. If you're working on a monolith, for example, you might have different scenarios, and then you won't have just one input disruptor and output disruptor. You will have probably more of them. But that also helps you, if you have a monolith and you want to break it into microservices, what you can do is use this design, and you will beautifully design your small services inside your monolith, and afterwards you can go and really do microservice architecture. One scenario which really helped me, I personally benefit of it a great deal. You all work with databases. And I don't mean now the fancy NoSQL databases, which we all like. We still have to work with SQL databases a lot. And in Java, we have a problem. The JDBC driver is, by its nature, synchronous. There are some efforts. The project ADBA, which is announced to come up in maybe next year, we don't know. But until then, all that connection handling for database is synchronous. And the only way we can manage that is to create bundled requests to the database. And when you have, let's say, you have an application which receives requests from the outside network, and you put all those events in a ring buffer. You can use this batching functionality inside it, and every time a batch is created, you will send to the database a bundled request. And in this way, you use only the connection available. So probably you know, with the database, you cannot increase the connection pool. So of course, you can increase it, but there is a specific number which, if you go above it, it won't work very good. So if you have to talk to a database and you have scenarios where you really have to hit it very often, this will help you a lot. And when you get a response back from the database, of course, you will have to unbundle that response and send it back to the individual users. Using this ring buffer, it's also very easy to monitor it, because you can always know how many events you have in the ring buffer. And this way, it's very easy to create that back pressure I was mentioning. Because if your request is overwhelmed, if your server is overwhelmed, you're receiving much too many requests, that ring buffer is going to fill up. And in this case, you know that, and the design I use, if you have microservices, is the following. So I really like Kubernetes. I like Kubernetes because it allows you to scale your application out of the box. All you have to do is have all these small services which can handle back pressure, And if you need more nodes, you signal that, and more nodes will be available for you. That is called upscaling. Why is that very important in the cloud model? Because cloud resources can be very expensive. And with such a design, let's say most of the time, you are very happy with one server, with one node. But sometimes, when you have spikes, you will need more nodes. And you will actually just pay for that limited amount of time, maybe minutes. You can really scale up with more nodes, as much as you need, and you will pay just for that. That's very important, especially for small businesses which cannot invest in hardware from the beginning because it can be very expensive. It looks like that. You have the services, they get upscaled, and when the load is over, downscaling will just reduce the number of nodes. When you use this approach, a very important thing is that the server you are using has a very fast startup. That's extremely important, because when you're overwhelmed, you cannot use a server which starts in, I don't know, 20 seconds or even worse. You really need your nodes right away. That's why I use, and I really recommend using the web server called Undertow. It's actually not just fast. Some people say it's the fastest web server in the world, even faster than many C++ or Node.js servers. Has anybody worked with Undertow so far? Do you know what it is? It's just a web server, just like Tomcat or Netty or any other web server. It's actually used internally by JBoss application servers or the current Wildfly versions. It's very reliable. It's very lightweight. It has under 1 megabyte in embedded mode. It fully supports blocking and non-blocking I/O, servlet for WebSocket, everything you can imagine. And it also comes with a few very nice features, which if you have time, I'll show it to you. So basically, Undertow is the web server I was using to build this example as well. In this case, I've used on top of Undertow JAX-RS. But you can mix it with anything. So if you are a Spring programmer and you want to use the Spring libraries, which you are used to, there's absolutely no problem. So you can just import in your POM all the Spring dependencies you want and start working with Spring. You might ask, or maybe you know, in a Spring Boot application, you could also embed the Undertow web server. Why not do that? The reason is, a Spring Boot application takes 2 or 3 seconds to start. The Undertow server takes less than 1 second. So IntelliJ is hiding this from us, but I can show you how fast it actually can start. I will stop this server. Where are you now? No. That was it. So fast can a web server written in Java be? And what I recommend regarding what project you're working on, always have in mind resilience. Anything you do, have in mind that you must know how to handle exceptions or error which can occur. Do you know this question? And this probably answers. Have you seen anything familiar? Does it sound familiar? The question is not if a failure would happen. The question is when a failure will happen. And we all know that most of the time happens in production. One more thing I would like to tell you. How many of you are working on microservices? A lot. Microservices are great, and they're really cool. But sometimes it's not the best idea to start a project directly with microservices. So your focus should not be what database should I use, what cloud model, what message broker, should I use Kafka, should I use RabbitMQ? No, you should start with designing your application, your model. And if you create an event-driven design inside a single node using, for example, Undertow, and you can go very fast, at some point, when a service starts to grow, then you can start thinking into splitting it into microservices. I don't see why you should handle all this complexity from day one, from the very beginning. When your application grows, you should go to a fully microservice architecture. But I don't recommend you to do it from day one. But what you should do is design everything in a reactive way, in an event-driven way. And in this case, you will always be prepared to go to the microservices direction. I just wanted to show you this picture. When you deal with microservices, I won't read it. It will take probably 10 minutes just to read everything on it, and I only got 5. Yeah. So when you are working with microservices, you need to take into consideration all this stuff in order to take care of resilience. And you probably don't want to do that from the very beginning. Yeah, I don't think we have much time. I will be around for the rest of the day. If you have any question, you can come to me anytime. Or if you want to share your ideas with me or talk about anything, you are very welcome. Thank you.